Today we will discuss SHM and waves. So there's kind of two things to this unit. There's something called simple harmonic motion, and then later we'll talk about waves, and it turns out they have a lot of similar properties, and so we throw them into one big unit. So the first topic is simple harmonic motion, which we abbreviate as SHM. It's oscillatory motion under a restoring force proportional to the amount of displacement from an equilibrium position. So let's kind of break this down. Oscillatory, meaning that it oscillates, it goes back and forth, and so any motion that goes back and forth, it sort of vibrates. And the reason it vibrates is that there's constantly this restoring force. There's constantly this force that pushes back. As soon as the thing goes one way, the force wants to push back the other way, and it pushes back, but now it has velocity, so it ends up going past the equilibrium point. And so now, because it's past the equilibrium point, the force pushes back the other way, and it's kind of going back and forth and back and forth. And we've kind of talked about some of this stuff before. And so you'll see what happens as our two main examples are springs, which we've discussed. Springs, as we know, you compress them, and then it wants to push back, and it'll push, and it'll gain speed. And then as it goes past the equilibrium position, now the spring gets stretched, and it pulls, and it wants to pull back to the middle position. Pendulums are similar. They just go back and forth, and constantly gravity is trying to bring them back to the center. But as they get to the center, they're picking up speed, and so once they hit the center, they have enough speed that they go up to the other side. And then once they're on the other side, now gravity wants to pull them back, and so again, there's constantly this restoring force. So today we're only going to do springs, though. We're going to do one day for spring, one day for pendulums. So springs, let's review what we already know, because we already discussed a lot of stuff. The first equation we discussed is back and forces, unit 3. The force of a spring is equal to negative kx, where k is our spring constant. So if you remember that k is how springy our spring is. Bigger spring means it's harder to, it takes a lot more force to move it. Less K means it's, more elastic, it's easier, more like a slinky would be less K. X is your displacement from the equilibrium position. And so however much you move from the equilibrium position, so say this is my equilibrium position here. If I move, negative 4 meters, that is my X. X equals negative 4 because I went to the left 4 from the equilibrium position. And then F is the force applied. And remember why this negative sign is here is because the force is always in the opposite direction of displacement. If I am to the left, my force is to the right, as the picture shows. And if I am to the right, my force is to the left. The other thing we talked about was energy. And so this was at the beginning of this semester, we talked about energy. The potential energy of a spring is equal to 1/2 kx squared. Again, k is our same spring constant. X is still our displacement from the equilibrium position. It's the same variables here, except for it's just a different equation. And then our potential energy is the potential energy stored into the spring. Let's get some extra terminology out of the way. So we have two things called period and frequency. Period, which we denote with a capital letter T, is the amount of time it takes for one oscillation to occur. It's measured in seconds. So to get a little confusion out of the way, T versus capital T. T is just constant. Like time is just constantly going on. And so, I could time a spring, and maybe a spring makes 3 oscillations in 12 seconds, okay? This is my lowercase t, okay? Because that's the total time that actually happens. T is my period. It's the amount of time for one oscillation to occur. So if 3 oscillations occur in 12 seconds, that means 4 seconds is the amount of time it takes for one oscillation to occur. So that means my period is equal to 4 seconds. Okay, so that's the difference there. T, lowercase t, is the total time that it's kind of like your stopwatch. It's the total amount of time it takes for something to occur. Or maybe it's a specific time, maybe it took 12 seconds for the whole thing to occur. I want to know the velocity at time 8. That's when you would use the lowercase t. Capital letter T is specific to a certain spring. It says, hey, how long does this spring take to do one oscillation? Frequency is the amount of oscillations that occur in 1 second. So it's kind of the inverse. First, we talked about the time it takes for one oscillation. Now we're talking about the amount of oscillations for 1 second. Okay, and it's measured in hertz, which you probably heard before. If you've ever heard about monitors, have something called a hertz value to them. This is their frequency. It's how fast they refresh, because in order for your screen to work, it's essentially a bunch of pictures that are refreshed over time. And so your frequency is how many times per second your monitor refreshes. That's how many oscillations occur every 1 second. Okay. And so they have this relationship between them. They're inverses of each other. So if you want to find period, you just take 1 and divide by your frequency. And if you want to, you can take this and you can solve for f, and you get that our frequency f is equal to 1 over t. And so if you want to get your frequency, you can just do 1 divided by your period. So let's try that. If I have a period of 4.3 seconds, what is my frequency? Well, my frequency is just 1 over t. So it's just 1 over 4.3. And so you put that in the calculator, 1 divided by 4.3, and you get 0.23, we'll round here, hertz. Cool. And so if you have the frequency of 0.27 hertz, and I want to know the period, well, the period is 1 over the frequency. So it's just 1 divided by 0.27. So 1 divided by 0.27 is 3.7. And this is measured in seconds. And so what this one meant is that 0.233 hertz means that one oscillation occurred, or it means that, hold on, I'm sorry. It means that, I'm blanking. So period is that 3.7, it takes 3.7 seconds for one oscillation to occur, okay? And then 0.233 hertz means that 0.233 oscillations occur every second. So it means that we made it that fraction of, like whatever that fraction is, if you wanted, to put this like over something, 0.23 is similar to 0.25, so it's similar to 1/4. And so we made it about 1/4 of the way through an oscillation in a second. So that's what hertz is. It's telling you how much of an oscillation occurs every second. Okay. There we go. Okay. So some more terminology. Now let's go to springs. Restoring force. We talked about that in the definition. Restoring force is the force that it's always in the direction towards the equilibrium position. And so in this case, springs, the spring force is always towards the equilibrium position. It's always towards the middle. It's always towards that position where the spring would just be in rest. Once you pull it, that spring wants to go back to that position. If you pull it the other way, the spring again wants to go back to that middle position. We call that middle position the equilibrium position, because if you were to just take the spring and set it there, it wouldn't move. The net force would be 0. Okay? And so we call it the equilibrium position because remember from forces, equilibrium means the net force is equal to 0. And so for springs, it means it's that position where the spring is not stretched or compressed at all. And if it is stretched or compressed, then the spring is going to try to restore itself to the equilibrium position. And so you can see this demo here. As the spring moves, the equilibrium position is the middle. As it moves away from it, the restoring force gets bigger and bigger and bigger. And as it gets closer and closer, it gets smaller. At the middle, there is none. And as it goes further away, again, it gets bigger. And so we can talk about some spring positions here. Let's just go through the motion. And we'll talk about a bunch of different things. Let's start with force. We know that the force is always towards the middle. And so here, F equals 0, because it's the equilibrium position. And then when it's to the right, the force is to the left. If we use Newton's second law, my bad, F equals ma, then we also know that the acceleration is towards the middle. Acceleration is 0 here, and acceleration is here because they're directly related. As F increases, A increases, and so on. They are proportional to each other. Okay? What else? What other variables do we have? We know velocity. At the max position, this is our max displacement. Imagine the velocity. If the block is moving this way to begin with, it moves this way, and then at this position, it stops moving to the left, and it's about to start moving to the right, which means that at this position, v equals 0. And the same thing at the max displacement to the right. In the middle, we have some velocity that's greater than 0. It depends on which direction you're coming from. If you're moving to the right, then the velocity is positive. If you're moving to the left, the velocity is negative, but it's not 0. And so that's why I put the absolute value signs there, because the absolute value of the velocity, the magnitude of the velocity is greater than 0. I just don't know the direction, which is the positive or negative. Okay? And of course, position. This is a position that's greater than 0. This is a position that's less than 0 because it's to the left, and this position is equal to 0. Okay? And so we have all these properties here. You need to make sure that you know the force and acceleration are directly related, and they're both in the opposite direction of the displacement. And then at the max displacement, v equals 0, and at the middle, you have the v is the maximum. At those max displacement, we have something called the amplitude. The amplitude it's the max displacement of the oscillating mass. The amplitude is telling us how far the spring moves when it moves at its greatest distance. And so if we have some equilibrium position here, let's say this x equals 0, and whenever we stretch or compress it and it starts moving, this is how far it moves to the right. We would call, maybe it's x equals 4 meters or something. We would call this the amplitude, and we would say the amplitude is equal to 4 meters. You could also get the amplitude from over here, because we know it's going to go to the same distance on the left side as well. But even though this distance, displacement is negative 4, we would still say that the amplitude is a positive 4. Amplitude is always going to be a positive number. It's just telling us the distance. Remember, distance is a scalar. We don't really care about direction. It's just telling us the maximum, really distance of an oscillating mass is probably a better word, but we use displacement. But we want the absolute value of it. With all that, we have some more equations. And so we've kind of studied the spring. We kind of know how it works. It's really not that complicated. It just goes back and forth. And so the acceleration is changing, velocity is changing, everything's changing, but it's a pattern that you can study pretty easily. We have a bunch of equations, though. And so let's show where they all come from. This one just comes from, we already knew that F equals negative kx. And so all I did was plug in Newton's second law, F equals ma, and we get this, ma equals negative kx. And so we can find the acceleration of a spring if we know the mass, the k constant, and the maximum position, or just the position at that moment. Okay? We can find the period of the spring if we know the mass and the k constant. All we need to know is the mass and the k constant, and we can plug that into this formula, and we get the period of a spring. You'll notice there's a 2 pi there. Yes, this is related to a circle. And so that's why there's a 2 pi there, because it has to, this isn't necessarily our radius, but it has to do with that. And so we get a relationship. We'll see that in a second when I show a video. And then the last thing is we need to use our energy, because we use the energy equation. And so I put this equation down, but you just need to know how to use conservation of energy. We can't leave it behind, okay? And so I wrote this down as the total energy beforehand and the total energy afterwards must always be equal, okay? And so for the most part, we're going to have springs that are horizontal, so it just means we don't really care about gravitational because we're on the ground the entire time. And so that's why there's no UG here. But if a spring is vertical, which there is a practice problem in the homework, so you can see it. If the spring is vertical, you also need to include gravitational energy into the equation. Okay? And when I say last equation, I don't mean like just the right side. I mean both sides. This is the last equation, this whole line. So let's try and one out. We have a spring constant K, so let's write that down. K is equal to 800 Newton meters. We have a mass mass is 8 kilograms. And we want to know the period. Well, I only have one equation that gives me period. Well, I have two actually. Period is equal to 1 over frequency, but I don't know the frequency, so that's not a very useful equation. I also know that the period is equal to 2 pi square root of, I always forget the order, so it's okay, you don't have to memorize this, m over k. M divided by k. Cool. So let's solve that. 2 pi times square root of 8 over 800. And so let's put it in the calculator. I'm going to write 2 times, if you don't know where pi is, at least if you have a TI-84, use the second button, which is the top left, the blue button, and then above the division sign, there's like this caret symbol, the upwards arrow, and if you look above that upwards arrow, there's the pi symbol. It's in blue, and so when you press that, after doing second, you should get 2 pi. There's other ways to get pi. If you need to, just Google how to type in pi on your calculator. Or you can just do 3.14. It's good enough. You can round there. So 2 pi times the square root of 8 divided by 800. And I get 0.628. And that sounds right to me. Times 2 times. Yep. Sounds about right to me. All right. And so that is how long it takes for this spring to do one oscillation, which is pretty fast. You know, that's less than a second. So the spring is going all the way back and forth in 1 second, or in 0.63 seconds. Here's a video. So if you want to watch this video, it's pretty good. It'll teach you a little bit about simple harmonic motion, but it's really just teaching you the relationship between SHM and circular motion. We studied about circular motion a while back, and objects moving in a circle. And it turns out there's this beautiful relationship between them. They're both related by sine and cosine waves. And in fact, if you really study, and if you go to college and you study simple harmonic motion and circular motion, you're going to have to deal with sine and cosine functions. And it's really not that hard, but if you haven't studied it before, you can't do it. And for the most part of you guys have not studied sine and cosine functions. And so we won't get as deep into that this year. But it's still a cool thing to see. You can still understand it even if you haven't seen it before. So it's a cool video to watch. We will cover pendulums next time. Have a good day.